which I better start recording. There we go. Okay, so you probably saw the email I sent out indicating the topics I was hoping to cover today. I suspect this is not going to be a full 2 hours today, because what I'll do is, as I indicated there, I'm going to start out by illustrating doing some simulations using the model that we constructed for ADAS-COG, so I can illustrate doing simulations when you use the approach we discussed for dealing with longitudinal data. So that's the first topic we'll do, so we'll spend some time on that. And the next is we'll get into a discussion of modeling approaches when you're dealing with summary statistics other than sample means. So we'll start on that, and that'll probably be as far as we're going to go today. That'll actually transition into what Jonathan will be discussing next week. So beginning next week, Jonathan is going to spend a fair amount of time talking about modeling summary statistics that you get describing time to event data. So that'll be his focus next week. So he'll take at least one lecture for that. So the current plan is he'll probably take one lecture plus a lab session to deal with that. Okay, so let's go ahead and jump into dealing with doing some simulations using our longitudinal model. And so this will be a follow-up then to the ADAS-COG example that I presented before. So just remind you what we had here. So we were looking at ADAS-COG scores over time in patients with Alzheimer's disease. And just remind you sort of what the data looked like that we were working with. So in that case, we were modeling this mean ADAS-COG change from baseline versus time for donepezil, galantamine, and rivastamine. And in addition, we also analyzed the sample standard deviations, or actually converted them to sample variances in here. The focus I'm going to have it will be on the means, in particular looking at population means, since usually the key inferences in development are not going to be related to inferences about sample standard deviations or variances, though the fitting process is enhanced by working with them. Our subsequent inferential process is likely to be based again around population means. So that's what I'll be illustrating, is the process of simulating those, and illustrate some of the kinds of simulations or even summarizations of those simulations that might be useful for making some inferences. And the way I'll look at it here is, I guess much like an example we did before for the where we didn't have longitudinal data, is we're going to look at comparative efficacy in this case for this. And what I'll do is I'll use donepezil 10 milligrams per day as our reference. So we'll do this with the perspective that donepezil 10 milligrams per day is the standard of care, and so imagine we might be developing a new compound that might look like, say, galantamine or rivastamine, or I suppose we might even be maybe we're maybe a third-party payer or an institution that has a formulary, and we want to make some assessments that way on what we might want to select as our as the drugs to include in our formulary, things like that. So there'd be various things, but either way, we're going to be looking at comparative efficacy. And the way I'll do this is I'll just take a look at galantamine and rivastamine compared to donepezil 10 milligrams per day. So that'll be our focus. So I just remind you of the model we were using, and this is the model not from your hands-on example, but for the one that we used as a demonstration in class. Let's see, where are we going? So we had we've got our normally distributed residual variation in here, and then we had our but again, it's ADAS-COG change from baseline. So we had a time component here, so we've just got a linear, in this case, an increase in the ADAS-Cog score over time, a little placebo component, then the drug effect, and then we have some various random effects in here that we're dealing with, both intertrial variation and inter-individual variation as part of the model. I won't go through all the detail again now, but I'm just giving you this as a reference point, because in our simulations, we're going to have to implement this same model that we did originally in BUGS. We're going to implement it in R. At least that's the approach I'll take. There's actually strategies we could use to even do it directly in BUGS, but I find those a bit cumbersome. So we'll go ahead and just code this up in R. What else did I want to mention? Again, these are the random effects in here. So we have to deal with our good old t-distribution and a normal distribution as part of this. And this is just a reminder that we converted this to an appropriate model, not for individual ADAS-Cog scores, but for sample means and variances. For our simulations, we could ignore all this stuff here about the variance, because we're going to be focusing on the sample means in this case. And actually, I should take that back. In a sense, we're not even going to be focusing on sample means. We're going to be focusing on population means. So in that context, what I'll actually be doing is really referring back to our individual data model as the basis for doing that, and essentially simulating a large number of individuals and taking the mean of those results in order to do the in order to get our population mean estimates. Let's see. Okay, not much more to say about that other than to just go ahead and implement it. So let's see. In my email, hopefully you saw that I did mention that I posted what's contained in this folder right here, this ADAS-Cog sim folder. So I sent out a zip file, which was just a zipped up version of that particular folder, which the main thing in here is this R script that I called ADAS-Cog sim.R, which illustrates doing those simulations. And the technique I'm using here is very closely related to the one I showed you before with that factor 10a example. So let's take a look at it. Okay, open that up, make it a bit bigger. Okay, so let's see what we got. Let's scroll. Oops, scroll all the way to the top here. Excuse me. There we go. Okay, so the approach here, like we've done in some of our other simulation cases, will be to go out and grab the posterior samples. There are MCMC samples that we generated using BUGS, and to build our simulations using those, because the idea will be is we're going to be trying to essentially take the posterior distribution of the parameters, and from that generate samples of the posterior distribution of our predicted values in here. So we're going to be looking at posterior distributions of these population means. So I'm going to have to go back and grab that information. So just go back to our files here. So in other words, I'm going to go back up to our directory here, the ADAS-Cog directory, and inside the further folder in here, there'll be this object here, ADAS-Cog fit.r save. So we're going to grab that and grab the posterior samples for our various parameters from that file. So some of this in the front then is some bookkeeping to tell the script where that is located. So, and we'll take advantage of the model name here for that. Example name I'm using to refer to our simulation example, so we can use that to construct our path back to where we've put this particular file in here, and then various bits here that we'll make use of. Like I did in the previous simulation example, I'm going to take advantage of doing some parallel processing here. So I've got this multi-process logical here that I've gone ahead and set to true. Again, if you, for some reason, that's not working correctly in your computer, or you just want to see what happens if you just do it on a single processor, you just set that to false. Then the usual nonsense here for setting various paths to different directories. So, for example, this model dir here, the model is the model directory, so that's containing that the file that has our samples in it, and then example dir is the name of the directory that contains this script. Let's see, is there anything new here? Most of the libraries we've used before. The parallel library is where we get the code needed to do the parallel processing across the cores on our machine. You know what? I've got MBT norm here. Now that I think of it, I don't think I ended up using it. That happens to be a library containing multivariate normal and t-distribution code, but as I recall, I don't actually use that, so we can ignore that. GData, I happen to use one particular piece of code. I'll try and remember to show you what that is. GData is a collection of stuff that I believe that's Greg Warren. I think the G is for Greg and Greg Warren's that he put together. It's kind of a miscellaneous collection of stuff, some of which is occasionally useful. Okay, so the basic gist of this is going to be, we're going to have, first I construct a function for simulating our population means given one sample from our posterior distribution of our parameters. So, and I'll come back to that in a second. So I write that to do that, and then further down in here at some point, here we go. We then go ahead and basically loop over all the rows in our posterior matrix. So we're basically looping over all of our posterior samples to construct then a posterior distribution for our population mean. So that's the basic gist. And then we're going to go through and take advantage of those to do some probabilistic calculations that might be useful for characterizing the comparative inference of these compounds. Okay, so let's step back to the function. Excuse me. So some components here. So P is just going to be, well, in fact, they're described here. So in fact, I'll make use of my descriptions of the different arguments here. So that's a vector of model parameters. And in our case, that's going to be basically pulling off one row from our matrix of posterior samples and passing that in as a vector. So that's going to contain our parameters. Design is the way I've set it up, it's a data frame that contains our independent variable values. In this particular case, those are going to be drug, dose, and time for what we're doing. And actually, I'll take that back. There's one more. I have the drug alphabetical in there, though I don't think I actually make use of that in here. I also convert it to an integer, 1, 2, or 3, depending on whether it's donepezil, galantamine, or rivastamine, and that gets passed in as part of that, and then dose and time. Number NSIM is, you can see here, that's the number of individual patients that we'll generate for calculating our mean. So the idea is you want that to be relatively large so that it's not going to be, it won't result in very much sampling variability in the mean. So we're generally talking thousands here, depending on how variable the data is. And then finally, this is something I introduced last time too, is I've got this intertrial variable, which allows you to deal with the intertrial variation in one of two different ways, depending upon what you feel that intertrial variation represents. So in the case where intertrial is true, then it's pretty much what it's saying right here. So that would indicate that we're treating the intertrial variation as a component of the posterior uncertainty. Whereas if it's false, what it does is it just averages the intertrial variability into the overall mean. So you end up taking a mean over the whole thing. Net result is that if it's true, you will tend to get wider prediction intervals than if it's false. Okay, so those are the components here. So, and the job of this function again is just to take that information and calculate a population mean for each row in the design data frame. So that's its job. Now, if you recall, when we had our model here, where do we go? We've got a couple of t-distributions in here to deal with. This particular form of the t-distribution is not built into R. R only has a built-in function for generating random samples from the standard t-distribution. In other words, it's basically a t-distribution with with a mean of 0, a scale parameter of 1, and then some specified degrees of freedom. So we have to, whereas the BUGS thing has one that actually allows the user to specify both a mean and a scale parameter in there. So we're going to have to come up with a way of doing that. It's actually pretty simple. And the way I set it up is I actually just generated a new function, so which is based upon the one that is built in, and it makes it look like most of the other random number generation functions in R. So it's got arguments of n, the number of random variables to generate, mu, so that is our mean, sigma is our scale parameter. I was going to call it, it's not quite the standard deviation, but it's very close to it in the case of the R distribution. And df with our degrees of freedom, and you can generate that then using the standard t, which is just RT, according to this. So you just multiply it by, you just generate a standard a standard t random variable, then multiply by sigma, and then add in the mean, and you're all set. Okay, so we do that. Part of our function here, recall there were these dref things here with different reference doses for each one of our drugs here. So I've just defined those. Those are just fixed values, not estimated parameters. And then we have the bit for how are we going to deal with our intertrial variation. And the easiest trick in here is, well, first of all, I'm taking extensive advantage of the implicit vector calculations that R does as part of this. And so the way I'm going to do this is if I'm going to be treating the intertrial variation as a component of my posterior uncertainty, then basically for each sample from my posterior, I only want to generate one sample from my intertrial variation. So if intertrial is true, I'm going to set this counter, this NT here, to 1. Otherwise, I'm going to be setting it to the number of simulations we're going to do. So, and what'll happen is, of course, if NT is 1, it means everything we do inside this one call to this function will take on one sample from the intertrial variation. Whereas if I set it the other way, we're basically just going to be averaging over all these n-sim values. So it's sort of, so in many ways it washes away. Again, it gets averaged out if we do it that way. So that's how I end up setting that up, and then I go ahead and generate the random samples then from my intertrial variation, where my count here is NT, which will either be 1 or N-sim in here. Excuse me. And these eta-intercept study, eta-drug, alpha study, those are the same creatures as you see over here, where you can see eta-intercept. Sorry, where'd it go? Here we go. Eta-intercept study, alpha study, and which one? Oh, eta-drug. Where is that here? Actually, I don't think I wrote it as eta-drug in this case. That's the way I implemented it here. Eta-drug. Just go back to this function here. The way I had, actually, where's my E delta? Where'd it go? Oh, I'm sorry. There it is right there. Eta-drug case. Sorry, I was getting off the beaten track there. So it is there. So that's just generating those. Then I'm sampling from my inter-individual variation. Now, in this case, because I'm going to end up averaging over all of these things for each time and dose and everything here, I don't really have to be real careful about keeping track of my individual subjects and what they look like over time, because I'm going to average them out here. So I can just sort of do this by brute force here. So, okay, so where am I going here? So, so my intertrial variation, and here's where I make use of that RT scaled function. So I've got my two individual specific random effects here. Because I'm now simulating these hypothetical individuals, I don't have to monkey with the sample sizes at this point. And then finally, the sort of the business end of calculating my predicted values is all going on here. So the things that are going on is we've got this S apply. You can see it's going for, it says 1 to the number of rows in the design. So what it's going to do is it's basically looping over the rows in our design data frame in here. So it's going to for each row, it's going to call this function where I've got my index I here. I'm going to have my parameters and my design, it's going to have our design data frame in here. The first thing I do is I pull out and just take on the first, I just grab the, where am I going here? Yeah, I just grab the ith row in that. So let me straighten out the indentation here. There we go. So subsequently, when it refers to design here, it's actually referring only to a single row data frame in this case. Let's see, and here it's the next three here, the details of that is it's trying gamma, E delta, and ET50 are all drug specific. So there's actually inside our parameter matrix, there's actually 3 values of each one of those. And so that's why I use this little grep thing here to get here. So when it does this, each one of these is actually going to become a 3-member vector in here corresponding to donepezil, galantamine, and rivastamine. And so that'll just pull those out. And then we've got our placebo thing here. So that's just, you can see how I'm using my parameter. I'm using a name parameter vector here. So that's why you see I'm pulling out the parameters by name, where the name is inside our indexing brackets here. So you can pretty much see that. You can see our, time is coming in here because that's part of our design matrix or design data frame. And then finally for E drug, here. You can see it's pulling out the dose again from our design thing here. Notice for things which are drug specific, like dose ref, it grabs the I drug value that we're going to be generating, the 1, 2 value of 1, 2, or 3, depending upon which one of the 3 drugs it is in here, and it does that for any of the parameters that are drug specific. In here now, in addition, what we've got is some of the up to now, most of the calculations I've done have involved scalars. But notice in here, get eta drug, which is a vector of n sim values. In here, let's see, are there any others? No, I think that's the only thing in the e drug. So when it actually generates this e drug value here, its e drug is going to become a vector of n sim values, whereas e placebo is just a scalar. Similarly, alpha and eta intercept. So yeah, alpha, eta intercept, and e drug are all vectors of n sim values in here. So again, what's inside these parentheses here will become a vector of n sim values, and then we're taking a mean over that to construct our estimate of the population mean. So that's the core of that. Just a reminder, notice nowhere in here do you see sigma for the residual variation. Now you could put it in there, but it's unnecessary because of the fact that, recall that if we go back to our original component here, our ADAS-COG change from baseline, our residual variation item is just a simple normal distribution. Well, of course, the mean of that thing is just this delta ADAS hat term right here. So there's really no reason to introduce the additional calculation of the residual variation. So it falls under the heading of it doesn't hurt, at least not much, but it doesn't help either. So we just skip that. And that's really, that's pretty much the core of that function then. So that function is then going to generate it's going to, well, let's see, every time you run this function, it's going to generate a vector of population means, and the length of that vector is going to be the same as the number of rows of our design matrix, or again, design data frame. Okay, so that's the basic function. The rest of this, I'm only including this parameters to plot, which I just copied directly out of the R script we use for running the model, just so that we don't have to carry around all those predicted values that we did in the original work. And that's what's going on right down here. This is grabbing, sorry, this load call here is grabbing the bugs fit object that was created. This nonsense down here is, I guess, doing two things. One, converting the results in the Sims array part to a matrix, and only taking the subset of those which correspond to the parameters to plot items up here. Okay, so now we get into actually doing the simulations. Right here, I've got two n's here. I happen to make them the same, but there's no reason why they have to be the same. The n sim is the number of posterior samples we're actually going to use to do our simulation. And then this n pop is the number of individuals to sample per population. This n pop is going to play the same role as n sim did in the function I just described. So I probably should have used a different name up there too, so that they didn't get confused. But and then I go through and set up that design data frame where I'm going to be specifying the drugs, doses, and times. So now we're going to be looking at comparative efficacy all relative to 10 milligrams per day of donepezil. So I only really need to generate a simulation for one dose of donepezil, just the 10. Whereas I'd like to look at a range of doses for galantamine and rivastamine, and so I've specified those, and there are different ranges here as appropriate for those drugs. And I'm going to do these for all of these for a range of times. Here I just, rather than doing a whole slew, I just sort of picked out some sort of landmark times. So we basically got 1, 2, 3, basically roughly 1, 2, and 3 months, 6 months, and 1 year is roughly what we're looking at there. So remember, these are in weeks. Maybe I should put a comment there. And here what I'm going to do then is just pull together a data frame here using the expand grid function here to get all possible doses and times together in here. So it'll do that, and finally at the end I use the drug name up here. So here I'm going to generate an integer to describe the drug. So 1, 2, or 3 corresponding to donepezil, galantamine, or rivastamine. So that's all that's going on there. You can ignore that one. I was just using that as a test. And then finally doing the simulation happens right here. And this if then else block is basically lifted right out of the examples that we've done before, where if you're using the multiprocessor, it sets up the cluster and uses the par apply function, whereas if you're not doing that, it just uses a standard apply function to do this. Syntax is almost identical for those, other than that you have to introduce this cluster specification argument in the case of par apply. So that's just going to go over, nsim, whatever, so where it's going to go grab nsim rows of that posterior matrix. So that's all this is it's going to be a matrix made up of some nsim rows of that matrix. It calls our 8s-cog CFB mean function that we set up. And then there are just the other arguments in here. I've got this written right now in the case where intertrial is equal to true in here. So we can illustrate, I'll actually illustrate both so you can get some idea of the scale of the difference that you might see. And that's the core of that. In fact, why don't we go ahead and run that much of it. Let's see, do I have an R? No, I don't have an R thing going here. Let's do that. Why did it do that? Okay. Okay, so let's just go, just run the part that takes us down to our simulation. With 8 cores, it doesn't take too long here. In fact, I guess I can never resist looking at the thing to see them actually all working here. And let's go, boom. Okay, come on. It should kick in pretty soon. Okay, there we go. So it's doing our simulations there. And okay, it looks like it's given all those processors back again, and I think it's actually finished. Let's make sure make sure I didn't make any errors along the way, none that are apparent. Okay, so we've simulated all those. So at this point, what we've got is, a posterior matrix, now, a matrix of posterior samples for our population means. If we take a look, for instance, at the thing we just created, which we called PRED. So we've got our 225 rows here happens to correspond to the number of rows we had in our design matrix, unless I made a boo-boo somewhere. And yeah, it does. And of course, we specified 1,000 posterior samples, so that's why there's 1,000 columns in this case. So the rows in this case correspond to each row corresponds to the same row in the design data frame, and the columns in this case correspond to the different posterior samples. So to look at a distribution to get some look at a posterior distribution, you could just look across any one of those. So for example, if I don't know, what is design, what is the first? Okay, so the first one corresponds to donepezil 4 weeks. In here, donepezil 10 milligrams at 4 weeks. And if you wanted to, you could even look at like let's go ahead and pull up a graphics window here. Yeah, you could even look at like a histogram, for example. We can see it. So if I wanted to look at, let's see, so this would be PRED, and I want the first column. Okay, so that gives you a histogram then of the describing our distribution of posterior mean, or we're looking at the posterior distribution of our population mean for ADAS-Cog change from baseline corresponding to donepezil 10 milligrams at 4 weeks following the start of treatment. So now we're going to take advantage of that in different ways to get a look at it. So here, rather than do the PDFs, I'll go ahead and do them on screen here. Okay, where'd my quartz window go? There it is. So we can go ahead and do these. So the first one is all I'm going to do is I'm just going to look at the dose response of galantamine and rivastamine and compare them, basically overlay them with the predicted response to donepezil 10 milligrams per day. So I'm going to plot like the median and 90% credible intervals for each of those, and again, just overlay them. So I'll just show you that. So there's an example right here. So you can see the blue here is, don't get it confused with what's going on with the galantamine dose here. The blue just represents our donepezil. So I've just put that across the whole thing so that you can basically observe where the donepezil dose response curve, sort of overlays that. So the red then is our galantamine dose response. Notice the panels correspond to the different time points that we did the predictions for. So you can get some idea how the two compare, and in particular, you can get a look at, how, you can get some idea of what might be an equivalent dose of donepezil, and how that might appear to be different as a function of time, for example. Same thing here for do the same thing here for rivastamine. So you get these overlays. Now, these make nice visuals, but I find it hard to make sort of probabilistic inference from this kind of a plot. So, these are, great things to show to a given audience, but if I want to say that, okay, well, that the probability of being superior to, donepezil 10 milligrams per day at a certain dose is such and such, that's not an easy thing to do just staring at this, though you certainly have an idea where what doses does rivastamine seem to be better than donepezil and vice versa. So let's take a look at it another way. So one is you can directly ask that question, what's the probability that the response for a particular dose of, say, galantamine is better than 10 milligrams donepezil 10 milligrams per day. So this is going through that calculation. Again, we're taking the same predictions to do that. Since we have all these individual predictions, that's a fairly straight ahead thing to go through and just grab a given, for a given row in our design matrix. I can go here and calculate, well, what fraction of the time is the predicted value for well, in this case, the predicted value for galantamine less than the corresponding prediction for donepezil 10 milligrams per day. So I'll get a bunch of zeros and ones corresponding to each posterior sample, and then I can just calculate the fraction of those which are ones, and that will tell me, that's my estimate of the posterior probability. That particular treatment is better than donepezil 10 milligrams per day with respect to the effect on 8S-COG. And here, let's go ahead and do that and plot that, because we're going to do that for each dose and time. And you get, in this case, you don't have bands because you're just calculating the probabilities directly, and you can plot those. So that's what we're looking at, and you're looking at it again. You can also look at it dynamically over time, since we've got a longitudinal model in here. And so you can get some idea. You basically know when you've got about a 50-50 chance of beating donepezil 10 milligrams per day at any given time point here. You also get to see that, okay, it looks like the time courses for these two drugs are a little bit different, because this probability plot actually varies a bit. The implication here maybe is that, gee, maybe galantamine's a little slower in onset or something here before it finally kind of catches up to donepezil. And then let's go ahead and do the same thing for rivastamine. We get another picture for that. This is a little bit different. It never goes all the way up to 1 like we were seeing with galantamine. So we can do things like that to more directly make probabilistic statements about the comparative efficacy. And the other one I did here is I went ahead and did the differences. And if you take a look at the code up here at the top here, you'll see it's almost identical to what I did above to calculate the probabilities, except right here, instead of having that calculating the fraction of pred values which are less than this pred ref, I just take the difference. It also means what comes out is difference, because each time it makes this call, it generates a vector, not a single value. So the thing you get out, instead of being overall being a vector, it's a matrix. And I further process that to take a look at posterior medians and 90% credible intervals. And we can look at that. Okay, and we get a picture something like this. So now we're looking at differences. One nice thing is by looking at differences like this, and these are differences within a trial, if you like, a hypothetical simulated trial. So you notice that compared to the bands we were looking at before, when we were just looking at sort of the absolute predictions, these seem a bit narrower because we've, we've reduced the impact of some of that intertrial variation by taking differences within a trial. And again, so we're looking at these differences. And here I've just put in the 0 here as a reference point, and I didn't overlay which is better and which is worse. But in this picture here, going down corresponds to galantamine being better. Going up corresponds to, or above that line corresponds to the donepezil being better. And I guess one last thing here, we'll just go ahead and do it for rivastigmine, and again, similar sort of picture. So that's a few things you could do. One that I didn't do here, but you could do just like we did in previous example, is I could calculate something like what's the posterior distribution for the dose of each compound here that is equivalent to donepezil 10 milligrams per day. So again, you could do other things like that as ways to communicate the comparative efficacy. Maybe one last thing to point out is I did run this both with and without the intertrial variation being a portion of the posterior uncertainty. So we're looking at the case where it is part of it. In fact, let me pull that up, the one I ran before here. So the pictures you're looking at, let's get rid of that thing on the left. Okay, so these are going to be the same as we were looking at, but now in PDF form. But now let's take a look at what happens if you average over that intertrial variation instead. Okay, this is probably the most striking comparison here, is to look at where we're calculating the ADAS-Cog change from baseline, and you can see on the right-hand side where we've averaged it in, you actually get quite a bit narrower prediction intervals for this example. And I guess whether you want to buy one versus the other is you have to sort of assess what you think that intertrial variation represents relative to the context you're trying to make inferences about. And it's not too hard to make a case for either one, which is perhaps bothersome that what may seem like subtle arguments can lead to such large differences. Again, that's galantamine. Did I? Okay, what did I do? Oh, I think I forgot to change. I need to check that. It looks like I forgot to change one of the labels here. This should actually say rivastigmine up here. Again, same sort of picture. Oops. However, it doesn't make much difference, fortunately, in terms of these particular comparisons. You can see these pictures are very close. I'm almost tempted to overlay just to see, but they're very close to each other. So it had rather little influence on this probability estimate. As I recall, that was also true for the other compound. It is. And it also didn't have nearly as marked an influence on the difference calculation. You can see here the widths of the prediction intervals are pretty close between these. So the actual measures that are probably more key to the inferences you want to make for this example, it really wouldn't have made much difference. Okay, that's a good point to catch my breath. I just wanted here to sort of give you some idea. We were sort of focusing so much on the mechanics of building the model. I thought we should spend a little time also on some pieces that, again, it's though there's some mechanics here, they're mechanics that lead to useful ways of interpreting the model in the context of something like a comparative efficacy assessment. So anyway, any questions or comments before we change topics? Oh, the question was, I see Danny asked, why would intertrial variation have no impact on some of these plots? It has to do with the fact that the last two plots here, this galantamine, here we're looking at difference between two compounds in this case, and in the other one it was looking at that probability, which again is a comparison between the two compounds. The intertrial variation is going to have far less impact on a comparative measure like that, because the way we're doing this is we're simulating. I guess you can think of this as being is kind of like looking at trials in which you've given the same compound. So in many ways, you've kind of eliminated the role of intertrial variation when you do comparisons. I expect I would see a similar sort of pattern if I was looking at ratios too, for example. So as long as you're asking questions about that have to do with things like differences, ratios, or in fact, almost anything that involves a comparison sort of within trials, uh, and then summarizing after you've done that, I would expect to see that the intertrial variation would have much more limited and just more subtle impact on the predictions. Whereas when we go back up to actually predicting the response itself, where it's just looking at a response in isolation. There's no comparison implicit in the quantity you're calculating. That's, you're kind of looking at an absolute value. So I don't know if that quite answered it for you or not. I mean, it would be similar to a situation where, you know, where if you had an outcome that depended very strongly on, say, a patient's condition at baseline, you might see substantially less variability in something like a change from baseline value than you would in an absolute value. So it would play a similar role there. Okay, well, why don't I scoot on to the next topic? Actually, you know what? The other thing maybe I'll do, I don't actually have a formal assignment, now that I think of it, for Monday for you. So maybe we need to come up with one. And maybe the simulation example would be a sort of a starting point to suggest one. So in your case, you had the ADAS-COG hands-on example. Now in that case, you were only dealing with donepezil and placebo. But you can do much the same thing, even given that limitation, you can do much the same things we did here. So why don't I suggest that you go ahead and essentially do the same kinds of simulations for that example, but now your comparison is going to be, again, is going to be donepezil at various doses compared to placebo. And so why don't you go ahead and do that example. Let's see, I'm trying to think if there's going to cause any problems with any of these. No, I don't think so. I think you can use all the same basic types of simulated outcomes we do here. The one that would not work well, which I did not actually do here, would be to try and come up with a donepezil dose that produces the same effect as placebo. Well, you can. It's going to be 0, but it's not that's not a particularly useful exercise. But you can still calculate. You can certainly predict the ADAS-Cog change from baseline. You can predict the fraction of times that donepezil will be, superior to placebo. In this case, it's going to be driven to 1 pretty quickly, and but it's still worth doing the exercise, and certainly the difference you would be able to calculate that pretty readily. So I'd say go ahead and why don't we make that the hands-on example that we can talk about this coming Monday. May also hit on a few other topics here. I'll think about that in the meantime. Okay, so let's move on to that next topic, as I said. Where's my slides? Let's go down to here. Right one, yes. Okay, so as I said, we've been focusing mostly on sample means, plus sample standard deviations is sort of of something that might augment that assessment. But that's not the way everything is measured. We often get things measured in the quantity that's measured in a trial is often not a nice, continuous value for which a sample mean is a logical metric. So let's look at some others kinds of things we may encounter. So let's start out with a pretty common one, and that's going to be a situation where the summary statistic you get may be the number or fraction of patients that experience a particular outcome or event in a study, and that can come up in a lot of contexts. So, and basically what we're talking about is summarizing binary outcomes. So as I say here, binary outcomes in individual patients are often summarized in terms of the number of fraction of patients with one of those 2 possible outcomes. Now those could be, their state of being at the end, or it could simply be an indicator of whether or not during the course of the trial some particular event of some type occurred. So that's why I say here, so such binary outcomes could include the occurrence of some event or an indicator variable for whether or not the patient benefited from treatment. And I give some examples here. So discrete events could be, death, myocardial infarction, deep vein thrombosis, adverse events, dropouts. So frequently, adverse events in particular is probably the most common situation where I end up using, using the kinds of approaches we'll talk about here to deal with whether or not a patient dropped out. Again, is another one that might be treated in this way. Other things is sometimes, even when you do have things that are maybe continuous measures or something, the result may get summarized in terms of so-called responder or remission status. In other words, each patient will be designated as having responded or remitted And then the summary statistic would be what fraction of patients were responders or what fraction were remitters. And, so again, these are measures, these would be essentially binary outcomes that reflect whether or not the patients achieve some degree of improvement. But again, those end up being binary outcomes summarized as number or fraction of patients. So if you're getting things in this form, well, as I say here, the appropriate likelihood function for the number of patients with a particular outcome would typically be the binomial distribution. And even if I have things reported as a fraction of patients that experience, I'll often convert that to a number so that I can appropriately use the binomial as the approach. Now, if you recall the binomial distribution, that's parameterized in terms of the probability of a particular outcome in an individual and the total number of individuals in here. So, so that would be, sort of a very logical distribution to use in this particular context. As I say here, that probability then it sort of plays a role similar to what the mean did when we're working with sample means. That probability P is going to be some function of our independent variables like dose, time, mean demographic parameters. Now, because P does represent a probability, it has to be restricted to the interval 0 to 1. But once we make that restriction, after that, it's difficult to generalize about what specific function you might use for P. Just like when we, it could be generated based upon a fairly large collection of possible pharmacodynamic models. Now, one approach that's commonly used for these contexts would be some variation on logistic regression, which basically just means that we're going to describe P using a Logit transformation. In other words, we're going to have, the left-hand side of the equation would be the Logit of P is going to equal some function which could take on values anywhere on the real line. So that would be a fairly common strategy. Alternatively, you could simply use a function you could just say P equals something where you've got a function that is naturally constrained to be between 0 and 1. So for example, variations on an Emax model could work if you restricted Emax above so that it can't exceed 1, for example. And other common variations would be things like probit, using the probit distribution, probit models where it's using the CDF for a normal distribution instead of the Logit transformation. Okay, so I guess maybe I'll just leave that there. Yeah, I'll just leave that there for now. We're not actually going to do an example right now. What it was just running through my head is, I think what I would like to do is after Jonathan does his session next week, I think I'd like to come back to some of these and actually do some examples to illustrate the approaches for these cases, rather than just let them sort of stand as a brief lecture like this. Now another, an extension to that binary case is what about when we're dealing with data that was originally measured on an ordinal scale, an ordered categorical scale. What do we do then? And in particular, I'm thinking of cases where you might have, the results reported as the number or fraction of patients whose results fall within each level of an ordinal scale, is one of the possibilities. So let's start out. Now, ordinal variables, they are often used to measure symptom severity or treatment response. And now frequently the results of those are actually reported as means. but occasionally they may be reported in terms of fraction of patients within each level of the ordinal scale. And I mentioned one option for dealing with such data would be to lump the levels together to produce only two labels. And then I make a reference to something you're not going to know what I was referring to. Because I say, as was done in the triptan example, and we'll come back to that in just a second. But anyway, if you did lump them together, you could apply the same approach as we just talked about for dealing with binary data, because basically you've just converted it to binary data in here. If you did prefer to retain all levels of the ordinal scale, then the numbers of patients within each level for a particular treatment arm and time can be modeled as a multinomial likelihood. So it's, sort of, again, a logical extension of the binomial. You go to a multinomial, and then the probabilities corresponding to each one of those levels then, have to be modeled. And one approach for doing that is to model that probability vector using a cumulative Logit model. So again, it's a logical extension of just the basic Logit model. Again, I'm not sure if I can crop up with a good example of this from the literature where I've seen enough data to do this, but if I can, I'll see if I can maybe cobble an example together on this. But now let me go back to my comment here just so you can see what I was talking about up here. Up here where I mentioned the triptan example. That the reason why you don't know what it is I replaced the triptan example in our motivating examples we talked about back in the first week. I replaced the triptan example with another one, but I put it back in for today just to illustrate what I mean here. I actually I put it back in its original location here, which is near the beginning. So let me show it to you. I haven't posted the slides yet with this added back in. Where'd we go? There we go. Boom. This is what it was referring to. That's not what I wanted. There we go. Okay, this is an article that we got Yapogen and I don't remember what Alderman's first name was. Anyway, they did published back in 2005 on looking at elatriptan, and particularly comparing elatriptan, which at that point was a new triptan, and comparing it to sumatriptan, which was the sort of the main one, sort of our standard of care on the market, and using model-based meta-analysis to compare the two compounds. Excuse me. So they were looking at elatriptan at the time, comparing the dose and time response of elatriptan to sumatriptan, and this just mentions the primary comparisons they're focusing on. One was the degree of migraine pain relief resulting from elatriptan 20 and 40 milligram compared to sumatriptan 50 and 100 milligrams respectively. There's also a thing in here where they were looking at the influence of encapsulation used for blinding on it, but that was kind of a secondary issue. The main issue was focusing on comparative efficacy of elatriptan and sumatriptan. So they did a model-based meta-analysis based on results from 19 trials. They looked at two summary statistics for migraine pain relief. And first we should mention what was originally measured in the patients was a 4-level ordinal scale. So basically they had, it was a scale that went from, no pain, mild pain, moderate pain, and severe pain in here. So that's actually the starting point where things measured in terms of that ordinal scale. But the metrics that they used for the model-based meta-analysis was to convert that to a couple of different binary scales. The first is what was termed pain relief, which they defined as improvement in the headache pain score from a baseline of either moderate or severe to either moderate, or I'm sorry, to either mild or no pain. So you basically got our four levels. If we call them 1, 2, 3, and 4, that means that, well, first of all, the entry requirement required that they have at least moderate pain. So everybody had a pain score of 3 to 4 at baseline. And so they're basically just asking, what fraction of patients converted to ones or twos. And then the other one which they talked about, was fraction of patients that were pain-free, where pain-free was defined as improvement of going from moderate or severe, that 3 or 4, down to no pain, or a 1. So those were the two metrics, and again, you can see they are both binary metrics now in the way they've done it that way, and so that the end result, they can report either fraction or number of patients, either with pain relief or who are pain-free. And this was, again, one they had longitudinal data up to 4 hours. Here's a depiction of this. So we're looking at fraction of patient on top. It's fraction of patients with pain relief versus the elatriptan or sumatriptan dose. And on the bottom, it's the fraction of patients who are pain-free, again for elatriptan and sumatriptan. So you can see what those look like let's see, the different curves correspond to different times. So let's see, what is it? I guess we're going from the lowest curves or the earliest times, and it goes up. So you've got half hour, 1, 2, and 4 hours in here. So again, so we've got our observed data with our model predictions overlaid on it. What do we got? Well, we'll skip the encapsulation. Let's just jump to this one just to sort of see how they ended up summarizing it to try and look at this. So the approach they used was to look at difference. Everything used sumatriptan as the reference treatment, and then looked at the difference between the result for elatriptan and that for sumatriptan. And you can see they looked at it as a function of time. And they did this, let's see, they got to remember which thing is which here. Okay, so the top curve, so we get this pain relief for the left-hand ones, pain-free of the right hand. The top panels correspond to comparing elatriptan 40 to sumatriptan 100, and the bottom are comparing elatriptan 20 to sumatriptan 50. So that was their reference points on both of those, and so they can look at those. Now in this case, anything greater than 0 corresponds to elatriptan being better than sumatriptan. So that was kind of the case they were making here. So we can see for the higher dose, for both measures, you can see the elatriptan shows up as being superior to the sumatriptan. For the lower dose, it looks like for pain relief, the elatriptan is still consistently superior to sumatriptan, and it's pretty much a wash when it comes to the pain-free measurement. Okay, and then their conclusions here that the meta-analysis confirms superior efficacy for pain relief and pain-free of elatriptan versus sumatriptan. There was the other thing again about encapsulation. Okay, so the point is that I didn't actually show the model in here, but you can see though they started out with a ordinal scale, they converted it to a binary scale and analyzed it accordingly. In this case, though I didn't show it here, it's a logistic regression model using a binomial distribution for the number of patients, as I recall. Actually, I have to double check and make sure that's the way they did it, but I believe so. Okay, let's jump back to where we were. Okay, here we go. Now we're going to move on to some counts here. So for some types of well, either efficacy or safety measures, we may be dealing with not whether or not a particular event has occurred, but how often a given type of event has occurred. So what we'll often get is something reported in terms of the mean number of events per patient. So this could crop up in a number of contexts. I mentioned a few here that I've seen, things like number of seizures, number of emesis events, number of adverse events. Now here I don't mean number of adverse events in the sense of number of patients with adverse events, but where they actually count up more than one event per patient. They may be counting more than one event per patient and maybe take an average or something like that. So anyway, so there are measures like that that might appear in the form of a count of the number of events. As I say here, most often that sort of data is summarized as a mean number of events over either the total study period or for maybe some periods between study visits as part of this. Actually, the one that I've been working on lately that I guess fits this would actually, that ties back to our triptan case, I guess, would be number of migraine or headache events is one that I encountered. Okay, so if we were actually modeling individual data of that type, typically what we would find ourselves doing is using something like a Poisson distribution or some over dispersed or zero inflated extension of the Poisson distribution to describe those outcomes. So, again, the simplest case, it might be something like a Poisson distribution where the mean event rate is going to be some function of various independent variables, including things like, dose, time, as well as the duration of the interval being part of it. Now, if you're dealing with a mean count, there would be different ways in which you could do it. I say one approach to modeling mean count data is to rely on the central limit theorem and just use a normal likelihood. And if it's reasonable to assume that the hazard for an event is approximately constant over time, then the mean should be proportional to the duration of the observation period. And that would be a way of dealing with the fact you may want to be looking at results from multiple trials, not all of which have the same duration. So you have to have some means for doing that. So that would be possibly one assumption you might be willing to make depending on the context. In addition, the variance should also be proportional to that duration and inversely proportional to the sample size. So you basically end up, if you use the normal approximation, pretty much back where we were when we were dealing with sample means for other types of outcomes. But I mentioned another alternative that you could use is rather than using the normal approximation, is you could take advantage of a property of the Poisson distribution. And that the property I'm speaking of is one where the sum of Poisson distributed random variables is also Poisson distributed. So in particular, I mentioned, I just put that sort of in mathematical terms. So if for each one of our counts here, our theta I here represents the count. If that's Poisson with some mean lambda I for all I, then when you sum up all of those thetas, that too is Poisson, and the mean is just the sum of all those other means. So it follows that if the individual count data are Poisson distributed, then the sum of those counts is also Poisson. And that sum can be calculated by multiplying the mean count by the number of patients. So that would be another strategy one could take as opposed to the using the normal likelihood. Okay, and then another category that we encounter quite a bit in clinical trials are trials where the original measurements were in the form of time to event. Certainly when we're dealing with things like mortality, morbidity trials, the outcomes are usually the time to something like, death, an MI, or some other event like that. And so they use, and there's a whole collection of tools used for analyzing that type of data when you actually have the individual data, and those are methods which have been designed in order to deal with the entire problem of right censoring. In other words, a situation where when you're dealing with time to event measurements, it's not necessarily true that everybody in the trial will experience an event at all. And so you have to somehow deal with the fact that you do have a subset of patients without those. In other words, what we term right censoring. So let's see, what did I actually write here? So the modeling of time to event measures that individual has to deal with right censoring. And unless an event occurs in all or at least a very large majority of the patients, a mean event time is not a very good statistic for meta-analysis in this particular context. So what do we do? And a comment on some of that without sort of finishing the discussion here, that I'm actually going to punt to Jonathan, who will be following up on this next week. Now, something that is often but not always available to you is that some publications may present the results of a time to event outcome in the form of a Kaplan-Meier plot that depicts the fraction of patients that have not yet experienced an event as a function of time. And so you could tabulate values from such a plot and use those values to construct a model. Unfortunately, for some, it depends upon the therapeutic area and the specific measurement you're going to be dealing with. But as I say, it's likely that most of the publications contributing to the database will not provide such plots. Tempted to back away from that statement a bit. For certain categories of outcomes, things like mortality trials, it's unusual that they don't put a Kaplan-Meier curve there. It usually would be there. But there are other things that you'll run into where it's not likely to be presented in the data. So it's variable, again, depending upon the specific context. But when it's not presented, then the data is more likely to be summarized in the form of something like the fraction or number of patients that experienced an event during the study period. And if that's the case, then you could just use binary data, describe, the approach we described previously for binary data, except that the probability for an event needs to be adjusted for the trial duration, given some assumption about the hazard time course. But then in the case where those survival or Kaplan-Meier curves are available, there have been a number of modeling approaches proposed in the statistical literature, and I give some references there, and those could be adapted for a Bayesian approach, as we've been doing here, but Bayesian or otherwise, there are strategies for dealing with that. I think that actually leads to, the lead slide for what Jonathan's going to be presenting next week, which is kind of where my curtain comes in here. So let me again stop, see if there's any comments or questions. And while I'm waiting to see if there's any, just remind you that we sort of came up extemporaneously here with an assignment that we can cover on the lab session on Monday, which is for you to make use of the results of your ADAS-COG hands-on example to do some population simulations based on those for comparing donepezil to placebo. Okay, I don't see anything popping up here, so I guess I will say farewell till Monday, and we'll take a little time to again revisit some of the simulations, and see you then.